All right, so the recorder is on, and let me show the clock. And it is here. We just stash it kind of here where it doesn't interfere with anything important. All right, and we'll check out the network connection. Hmm, okay, and a few more things. All right, all right. So we haven't met for a whole week. I hope you guys had some time to review the material in addition to getting the homework assignment done. So what do you guys want to do? Do you want to go over the homework assignment, or is it okay? We got okay. So we'll go ahead and do that. All right. So the homework assignment is down here. Loop assignment. Okay, that's due today, and the due date is like a few minutes ago. So we're gonna open this up. All right. And this is the code that you need to trace. So the question is, what does it look like, after you trace it? So what I'll do is I am going to use Google Sheet for this. And the nice thing about Google Sheet is I can put it into the shared drive that you guys all have visibility to. So this way, as I'm working on it, you can actually look at it if you want to. All right, so let me go to CISP 300, go to the shared folder, and then create the spreadsheet in this folder. Okay, and it's going to be called, using today's date, which is 2025 02/19. And so that I don't have to kind of switch between the two screens all the time. I'm going to move this into a new window and display this, on the side. Well, actually, I changed my mind. I don't need to do that. Instead, I will go to this homework assignment here, and I just need to copy and paste this portion to a part of the screen that I can see all the time. And I think I remember the rules that need to be followed, so I think I'm okay with that. So this is what I'll do. Just use a screenshot tool, take a snapshot of this, open the bitmap on its own, and then I can now switch to the spreadsheet so I can actually trace it in the other sheet. So that is this one here. There we go. All right. So we're gonna go by all the same rules, which means your column A is almost all the time going to be the line number, and then we need one column for each variable in the code. So this is the code here. We have two variables. So we have one for X, one for Y. Which one is the one to the left-hand side? Which one is the one to the right-hand side? Really does not matter, okay? As long as they are both here and you are using those columns consistently, you're fine. And then we have comments, okay, which is actually pretty important in this particular trace. And by the way, the recorder is on, so just in case you want to focus more on the actual tracing instead of trying to copy everything right now. Okay, so I'm gonna shrink the columns a little bit here. Okay, so the program, or at least the homework assignment, does not tell you anything about X or Y ahead of time. So that means you need to indicate that as the precondition. So the precondition has to specify that X and Y, they both start with unknown values. Okay, you were not given any specific values in these variables. Yes, go ahead. Mm-hmm. Mm-hmm. Correct. The precondition is what you know before the first line that is available in the code. Yep. So unless the question or unless the homework assignment specifically say, okay, assume variable x has a value of this and variable y has a value of this, then they're unknown. Yeah, hmm that is correct. And that's why we use the word pre here because it is a precondition for the entire algorithm, which yeah, which is trying to tell us what do we know before line one executes. Okay, all right. And there's no need to leave any comments here. If you have comments, that's fine, but you don't need to have comments over here. So I'm just going to leave myself a little bit more space for the comments. So here's line one, and after line one executes, we know x would end up with a value of 5, so we put a 5 here. After line two, we know y ends up with a value of 2, so we put a 2 here. And then on line three, we have to evaluate a condition, which is x is greater than 0. So the simplest you need to do is to indicate that x is greater than 0 is true because x has a value of 5. 5 is greater than 0 is true. Okay, so that's kind of the minimum that you need to do is to tell me, how the condition evaluates. Does it evaluate to true or does it evaluate to false? Now, if even better. Yep. So you can describe even more and say that because x equals to 5, therefore x is greater than 0 is true. That's even better. Okay. I definitely not a problem. Okay. You can include more information in your trace just for your own purposes, just so you know why the condition evaluates to true. That's fine. Okay. Not a problem. And because of that, now we move on to line 4. So line 4 says we want to subtract 1 from x. So x is now going from 5 to 4. And then on line 5, y gets y plus x. So we're looking at the current value of x, which is 4. So y is 2 plus 4, which is a 6. Okay, so we put a 6 here. No need to leave any comment for these lines for the assignment statements. We don't need comments anymore. And then the next one is important because this is a loop. So where do we go to? We go back to line 3. We go back to re-evaluate the condition. So in this case, x is greater than 0 is still true. So in your trace, if you say because x is now 4, but 4 is still greater than 0, that's fine. Okay, it's just adding some additional comment to explain it to yourself is perfectly okay. Okay, but this is the minimum. Okay, what condition did we evaluate, and what is the value that it evaluates to? So because the condition is true, we go back to line 4. We subtract 1 from x again. So x becomes 3. We go to line 5. And this time we have 3 plus 6. So the value of y goes to 9. And then we go back to line 3 again. So at this point, it is kind of boring because it's kind of doing the same thing over and over again, so to speak. So now it's down to 2. And then on line 5, this is 2 plus 9, which is 11. And we go back to line 3. X is greater than 0 is true again. We go to line 4. We decrement to 1. And then we go to line 5. And line 5 is adding 1 to 11, which will give us 12. Then we go back to line 3 again. And x is greater than 0 is still true. Okay, so this is one trick that I want to show you too. There's a little bar here, and this trick works for just about any spreadsheet program. So you can be using Excel, you can be using LibreOffice, you can be using Google Sheets. They all kind of have a similar feature, which allows you to move um, this line down. So this way, when I'm scrolling, you can see how the top does not scroll. Okay, now you may not need to do this because more likely than not, your screen has more resolution than the projector, which means you can display the entire sheet without having to scroll the bottom part without scrolling the top. But in my case, because this screen is only running at 1280 by 720, I cannot fit that many lines on the screen, and as a result, being able to do this is really helpful. All right, so we go to line 4 again, and this time x is decrementing from 1 down to 0. Are we done? Do we go to post right now? No. because we still have to go to line 5. Line 5 is right after line 4. There's no decision point to make here. So line 5 is actually going to put 12 back into y, okay? So now we go to line 3. Do we just exit right away? Okay, you have to still evaluate x is greater than 0 is false. So in your case, you can say because x equals to 0 and therefore x is greater than 0 is false, that's perfectly okay. Yes, you should put a 12 here because it is still an update. So every time you have an assignment statement, even if it is the same value that you're using to update it, you should still put a value in that cell just to know that it is an update, even though it's updating to the same value. I won't take any points off you for this time, but in the future, it is important to do that. So now, okay, after line 3, this is when we get to post right away because there's nothing to execute after line 3 when the condition of line 3 is false. Is that okay? All right. Okay. So if you guys have additional stuff in the comments, that's fine, not a problem. Okay. But this is kind of the minimum that I'm expecting from this trace. All right. Are there any questions about this homework assignment? Hmm? Oh, you mean just to copy this is now a 0 and this is a 12? That's fine too. You don't need to do it. Yep. Hmm. All right. Any additional questions about this homework assignment? Was it time consuming? It took us today with certain explanations in between about 10 minutes to do it. So was it a lengthy homework assignment for you? Because you have to look at the flow chart just to figure out what to do next and so on. Okay, not really. Okay, excellent. All right, so this is now in the shared drive, okay, which means you can refer to this for studying purposes, just to understand what is the standard and how we perform the trace. All right, so if there are no questions, we're going to move on to the next topic. Yes, go ahead. The shared drive is, I don't know whether the link is working or not. So let me close this tab first. So if you go to the top of the Canvas shell, there's a link to the shared folder, but sometimes it doesn't work. In this case, it does work. So you just click on share folder and that's where you find all the files. Some are from way back, okay, because 2019 fall was the last semester that I taught this class. I don't usually teach CISP 300, these days anymore. But because Momena, the instructor who was originally scheduled to teach this class, because of certain issues with her employment status, we had to, I have to step up to teach this class for her. All right. Any other questions before we move on to a rather difficult concept, but it is an important concept. So we all good here? All right. So I'm going to, I don't need to close the folder. We'll just keep it up, but I don't need this part anymore. And then the clock has hidden out of view. So let me go back and make it reappear. I don't know where the clock is. Um, hmm, I don't see the clock at all. All right, well, that's okay. We'll just restart. No, it's still here. Okay, I can close it and restart it because I forgot to make the clock always on top. So I just have to remember to do that. Alrighty. So now we're going to move on and talk about pre and post condition. Okay, I'm not sure whether any one of you had the time to read it a little bit ahead of time. Okay, it is heavy stuff. Okay, it is definitely a lot of math in it, but it is important because um, many of you already know that AI can write code, right? AI can write program code. Um, so now the question is, can you specify what the AI is supposed to write? In other words, what is the program supposed to accomplish? That becomes the important task. Okay, if you can correctly describe what a program is supposed to do, chances are with simpler problems, the AI can write the code for you. Then the bigger question or the most important part is, can you describe what the program is supposed to do? So if you use English words to describe what a program is supposed to do, it is usually kind of vague. It is usually ambiguous. Okay, and so the AI engine, which is called LLM, most of the AI is related to LLM or large language model. It can understand you as much as the next person can understand you. But we all know that natural languages does not even depend on which one, always has ambiguous points. Okay, because where you put the punctuation changes the meaning of a sentence. But we don't specify the punctuations when we speak. And oftentimes when we write, we also do not use the proper punctuation at the right places. So that means when use natural language to describe what the program is supposed to do, a lot of times it won't give you the correct answer. So that's why we are in this folder, or not in this folder, but in this module, we talk about how to use mathematics to prove that a program is doing what it is supposed to be doing, or it is using mathematics to predict what an algorithm will do. Are we doing okay so far with that concept? Okay, because ultimately what we want to do is to have the AI to help us prove once and for all that an algorithm is accomplishing what it is supposed to do, no more and no less. Okay, that is important because if we don't do something like that, then we can end up with problems. Okay, so there are certain problems like this one. It's called you can look it up. It's called hard bleed, not hard bleeding, just bleed, hard to bleed. So if you go to the hard bleed bug site, okay, which is its own website here, you don't have to understand network security or what is encryption and whatnot. Suffices to say that this bug or this problem exists only because the program was written by people and they forgot to check a few things. So that allowed a maliciously formatted request to look into the memory space where it really should not have access to. And the end result is with this bug in place, it is possible for someone to break into a website, look at all the SSL encryption key, and be able to gain access to information that the hacker is not supposed to have access to. So that's kind of the bottom line. Okay. So the reason why I brought this up is because this problem could have been avoided completely if we have automated program verification. So program verification is the computer, the AI, okay, so to speak. AI is always just in quotes, okay, because it's just a term that we use to refer to things that we wish computers can do, but they cannot do just yet. Okay, that's kind of about the boundary of AI. So we want the AI to be able to prove using rigorous mathematics proofs you know that one, we can specify what the program is supposed to do and what it is supposed to do with the mm, uh, the packets or the requests that are not formatted correctly. Okay, so they should be rejected. Um, and then we can prove once and for all, without using test cases, that the program does what it is supposed to do all the time. Okay, so that's kind of the holy grail. Okay, that's kind of the holy grail right now in computer science because cybersecurity is becoming more and more important. And as a result, people are now focusing more time to make sure that the code that people write or the other AI write is doing what it is supposed to be doing, and no more, no less. And we want to prove all that stuff without throwing test cases at the program. Because if you rely on test cases, it is always possible that you forget about certain test cases. Okay, and those are the problems. That's when we have cybersecurity issues. Does everybody kind of understand the context of this part of the class. It is math, exactly. Well, it's the rigorous math proofs that is important. And that's one of the things that AI really cannot do just yet, is theorem proving. Um, yes, yes. AI can quote unquote write code. The way it writes code is the same way that it can generate text when you ask it about a question. So AI is okay. Let me be more specific. LLMs like ChatGPT or DeepSeek, they are very knowledgeable because we use a lot of data to train these AI, but it cannot actually do reasoning as well as people can, which is kind of interesting. Okay, so even with the O3 model from ChatGPT, it is still not entirely 100%, when it comes to logical reasoning. And theorem proving is also kind of more difficult, from the perspective of LLMs because that's not how they're designed to work. So this is, I think it is important. Okay, it's an important topic. It used to be a very important topic in the 90s. People were really obsessed with automated theorem proving, but at that time, computers were very, very slow. Okay, and you guys may ask, how slow? Okay, how many people know what is Moore's law? Moore, Moore's law. Okay, so we'll look it up. Okay, this is also something that is important. If you're into technology, this is a very important thing to understand. So Moore's law is not exactly a law; it is just an observation. So it says, the number of transistors on a microchip doubles about every 2 years, with a minimum cost or no cost increase at all. So what does that mean? Yep. Well, I mean, everything improves over time, right? If you look at like automotive, okay, like a car, a truck, okay, from let's say the 1940s, okay, we had internal combustion engine back in 1940s. We have diesel engines back in 1940s. So are the cars, the engines that we have these days, okay, in 2025, are they better than the cars in 1945? They're probably twice or at the most 3 times as efficient. Okay, your cars can go faster, they're more reliable and so on. But we are looking at the most, okay, maybe a few 100%, okay, of improvement. So when you look at technology, when you look at semiconductor based technology, what is the kind of improvement that we see? So we so I'm gonna switch to my tablet. I just got my new tablet working, hopefully, and we'll see whether it works or not. It's not working yet because I have to turn it on. Can you what? Um, yes, you can, but yeah. Okay, alrighty. Yes, in the future, you can just go. There's no need to ask me. Mm-hmm. So it's 81048080. Click OK, and hmm, I think my networking is. There we go. All right. I'll do one more time. There we go. Okay. So slightly new setup. Okay. So let me ask you how many 2 years have gone by since 1945? Okay. So this is 2000, oops, wrong tool, 2025. And then we subtract 1945 from that. Okay, that's a zero. 2 minus 4 is 8. Okay, so 80 years has gone by. Okay, I hope my arithmetic is correct. Okay, but 80 years sounds about right. Okay, so now the question is how many 2 year periods are in 80 years? Well, that's an easy one. 80 divided by 2 is exactly 40. Okay, yes, it's not showing up. Darn. Okay, So I'm not sure why that is the case. Let me try to refresh it. It lost the connection. Oh, it's my tablet's turn to lose its internet connection. All right. Hmm. All right. Well, okay. I still have to improve the reliability of this technology, but for the time being, I'm going to use the whiteboard. So we have 80 years divided by 2, that's 40. So we have 40 cycles to apply Moore's law. Moore's law says every 2 years things will double. Okay, we're talking about doubling the density of a chip. So the question now is, if you compare a computer in 1945, okay, which is basically where when Alan Turing, worked on his Enigma cracking machine, to crack encryption. So how much more transistor can we fit in a computer today compared to a computer back in 1945? How many times are we talking about? So let me give you some math here, okay? From 1945 to 1947, it doubled, right? Every 2 years. From 1947 to 1949, it doubled again. And then to 51, it doubled again. To 53, it doubled again. So if we just look at from 1945 to 1953, how much, how many, what is the percentage increase, or what is the fold of increase of density of a computer? 16 is correct because it's 2 times 2 times 2 times 2. 2 to the power of 4 is 16. Okay, so now let's just say that it's from 1945 to this year, 2025. There are 40 cycles in between. So that means the computer today can fit approximately 2 to the power of 40 times more times transistor compared to a computer back in 1945. There is no technology that we have seen ever that has this kind of improvement over time. Okay, and this is why everything is possible. Okay, if we had no advance in avionics from 1945, we will still have drones today because we will still have computers to run the drones. Okay, if we had no advances whatsoever with automotive technology, we'll still have self-driving cars today because the control system is silicon based. Okay, you will still have a lot of pollution. Okay, they're not electric cars, but we will still be looking at self-driving cars and drones and all the technology that we know. Is that okay? All right. So what does that have anything to do with what I just talked about? When I was in college, it was 1985. Okay, so we are looking at 1985, and in between, how many years has passed? 40 years. Okay, so 40 years has passed, which means we are looking at 2 to the power of 20. So can someone quickly tell me approximately what is 2 to the power of 20? It's a base 10 number. It's about a million times. Okay, which means in 1985, there are certain ways of doing things that is simply impossible because computers were slow and storage was precious. Okay, we are looking at 20 megabytes on a hard drive. And a hard drive is the size of a 5.25 inch width and a full length, kind of thing, and the height is about this much. Okay, so we are talking about really clunky technology that has fairly low performance compared to what we have today. You can easily buy, a what 2 terabyte drive now, and it comes at the size of a chewing gum stick or slightly bigger. Okay, but we're talking about just the order of magnitude. Yeah. So computational resources has changed dramatically just within 40 years. Not even looking at the 80 years that I was looking at earlier. So that means certain things that was not possible, even though the method was correct, but technologically speaking, we simply did not have the resources to do. Now we do. Okay. So that's the reason why this entire topic is resurrected. Automated program verification. Now you don't have to take my words for it. Okay, you can look that up. It's called program automated verification. It's a pretty interesting topic, and there are a lot of research interest in that topic these days. All right. So what we are going to talk about now is related to this. Now you also have to remember between today and the time that you graduate with a bachelor's degree, it's approximately 4 years. Okay, because you have to spend about 2 years here to complete your computer science associate degree, and then you have to transfer and then have another 2 years at a four-year university. So we are looking at 4 years. 4 years is two of these Moore's law cycles, which basically means computational resources wise, everything would be 4 times. Okay, in terms of capacity, in terms of processing speed, there'll be 4 times what we have today. Okay, I think at that time it would not be unreasonable that a small LLM, or basically that's oxymoron. Okay, because large language model. So a smaller language model can probably fit inside a Fitbit within 4 years. In other words, you don't need internet access. You don't need to Bluetooth connectivity with your phone. You can just ask your watch what you would ask today in an LLM. Okay, I think that's possible in 4 years. So that being said, okay, we are looking at a very interesting future. Okay, I really cannot predict what's going to happen in just 4 years. So we will start with what is this crazy math, okay? Because there are many people who get into computer science who are startled by the amount of math they have to understand in a class, okay? Eventually, so there are two schools of thought regarding the role of mathematics in programming. One school led by Esther Dijkstra, he passed away some times ago. Suggests that the programmer should be a mathematician first. Now there are different branches of mathematics. There's pure math, there's applied math, and there's a lot of stuff in between. Okay. In order to get your computer science associate degree, what classes do you have to take in the math department? Right. But from the transfer perspective, it's Calc 1, 2, okay, which is basically Math 400 and Math 401. Those are required. Yes. Yep. And depending on which one you transfer to, they might have even more math requirement. So if you're transferring to any Cal Poly, for instance, or Berkeley, they would require even more math classes than just Calc 1 and 2. Okay, so calculus is interesting because it is not really used a lot in programming, but it is nonetheless mathematical reasoning training, which is actually kind of important. Hmm. Right, right. This class is more of an exposure, so we don't dive really deep into the mathematical side. Right, it is an exposure. Um, and this is kind of funny. I have not done this for a while. So if you look up cruelty computer science, let's see what we'll find here on the cruelty of really teaching computer science. So this is where Dijkstra wrote his article on whether mathematics should be taught before programming. Okay, now I'm not going to read the whole thing. Okay, I will leave it up to you guys to read the whole thing and kind of use it to help you make decisions. Okay, because um, I think even though there are different schools of thought, this one is, I think it's kind of upholding so far. Another school of thought, which is led by Donald Knuth, and these two were basically the giants of computer science and modern day computer science. And Knuth is still alive. Okay, he was a professor at Stanford University, and he's still pretty active. Okay, so you can look up his name and find out what Professor Knuth has been doing these days. So this guy, okay, Dr. Knuth, Professor Knuth, thinks that with advances of tools, we can probably have people who are not exactly very good at math to participate in computer science and code development. That's his thought. Is with the improvement of tools, people do not need to know as much about mathematics in order to write code. Okay, so that was true. Okay, so if you look at the graph, this is my belief. Okay, this is just me. So if you look at the graph, okay, and look at how much math is needed in order to be successful in computer science, from 1940, I think 7, which is when Alan Turing completed his. Do, does anyone remember what year Alan Turing finished his computer for cracking the encryption of the Enigma? I think it's somewhere around that time. Okay, so we'll just call it 1947. So the amount of math that you need to become a computer science is pretty high. Let's say this is 2025, and we'll just say this is somewhere in between, which is 1985. Okay, so I would say that curve kind of dipped kind of significantly, but now it is going back up again. It's going back up again because even though AI or LLM can write the code, you need to specify what the code is supposed to do. And that turns out to be somewhat of a challenge. Okay. Um, I teach CISP 440 also, and that's basically a math class. So in that class, we looked into how difficult is it to specify an algorithm that would sort an array. Okay, so you don't have to understand what is an array because we haven't talked about it yet. But if you think about sorting, like if I give you a deck of cards that is not sorted, and I ask, okay, this is the ordering, okay, between all the different cards. Do you know how to sort it? You go like, yeah, I know what I'm supposed to do. Okay, if you give me a deck of cards, I can tell at least whether it is sorted or not. But as it turns out, in order to describe precisely what sorting means, is not easy. Okay, and in CISP 440, that's one of the first topics that we talk about in that class is how do we mathematically specify the result of a program that is supposed to be doing sorting. That's all it is. So anyway, I'm not taking a particular stand, okay, whether mathematics is actually required or not, but I'm giving you guys some exposure. So the concept of a pre and post condition is to specify after the execution of a statement, if we know the precondition prior to the execution of a particular statement, can we deduce the condition that has to be true after the execution of that statement? So it'll be done statement by statement, and then we'll look at the nesting structure of the program of the algorithm. And the bottom line is, can we derive from the precondition of the entire algorithm, start with that, follow the code mathematically, and come to a conclusion of what is the post condition of the entire algorithm? Okay, so that's kind of the purpose. And this class, once again, is just an exposure. So we'll start with something that's simple, constant assignment. So we'll look at this algorithm that only has constant assignment, which basically refers to the right-hand side always being just a constant. It does not mention any variable. So I think we should be able to follow this code at this point. Is that correct? Okay. But instead of a trace, Now we want to look at the precondition and the post-condition on a line-by-line basis. So let me just kind of copy this one first because I want to be able to refer to this as I scroll down, and through the explanation. So we're going to make this always on top because I need to refer to the lines. Okay. All right. So this particular notation, pre-1, is basically trying to say what is the precondition of line 1? In other words, what do we know for sure before line 1 executes? Most of the time, I would tell you nothing about the variables, right? In other words, in a trace, the pre-line would be all question marks. So now the question is, what is going to be true when we don't know anything? Well, it's going to be true itself. Okay, so the precondition of line 1 is simply true. Okay, which says absolutely nothing about what do we know about the variables. But that's kind of the whole point. Okay, is we don't know, we don't make any assumptions. Then we ask what is the post condition of line 1? In other words, after line 1 executes, what do we know for sure? What do you think? Exactly. So yep, so exactly. So after line 1 executes, we know for sure that x equals to 0. But we also know that, other than that, everything that we know before line 1 executes is still true. So that's why, we get down to this portion here. The post condition of line 1 is the precondition of line 1, but on top, we also can now say, oh, by the way, x equals to 0 also. Now, because the pre-1 is true, so true and whatever is specified on the other side of a conjunction is just whatever is on the other side of the conjunction. All right, what does that sentence even mean? Mhm. All right, so I'm going to use the whiteboard again. To the people who are missing the in-class, portion, I guess they just have to show up a little bit more often. So when we look at the truth table of conjunction, so we have x, we have y, and then we have x and y. And the and is also I'm also switching to use the mathematical notation for and, which looks like a little wedge pointing up. Okay, so that's the mathematical notation for conjunction. But in the truth table, I'm just going to use the regular C++ notation. So there are 4 entries. Okay, false, false, and this is going to be false. I'm using 0 to represent false just because it doesn't take as much to write it, and then 1 is representing true. So false and true is also false. True and false is false. The only time you have true is you have true and true. Okay. So other than I'm switching to use 0 and 1 to represent false and true respectively, that's the truth table that you have seen already when we talked about conditional statements. Okay. If you look at that truth table and you do not recollect that we have talked about this, that really is an indicator that you might need to spend more time to study and jot down some notes because we have talked about conjunction already and the truth table is already presented. Okay. Okay. So what does that have to do with anything that I was just mentioning? Well, what I was mentioning is what if we know that x is true? Okay. Y can be false or true. So we are looking at the bottom 2 rows here. Okay. So you can see that with the bottom 2 row, whenever x is true, then x and y is really just whatever y is. Is that making any sense? It is almost exactly the same thing as 1 times x is just x in algebra. Is that okay? So that means in the discussion here, when I say the post condition of line 1 is whatever the precondition of line 1 is, but on top we now know x is equals to 0, then we can just simplify the whole thing because pre-1 is true in this case, so we can now simplify the whole thing so that post-1 is just x equals to 0. Are we doing okay so far with that part of the math? Now, it is Boolean algebra, which is not supposed to be the topic of this class, okay? But at the same time, it is also not Boolean algebra because using a truth table, we can come to the same conclusion. Are we doing okay so far? How the truth table allow me to convert true and whatever to just the whatever. Because in the truth table here, if one side is true, then the other side determines the exact outcome of the conjunction. No. If one side is true, if x is true, then y is the same thing as true and y. So we can simplify. Yeah. Are we okay with that concept? All right, more or less. All right. So now we say, okay, what about pre-2? This is line 2. Line 2 says we want to store a value of 2 into variable y. So the precondition of line 2 is the same as the post condition of line 1. That kind of makes sense, right? Because after line 1 and before line 2 is exactly the same thing. Okay, does that make sense to you? If I need to know exactly what is true right after line 1 executes, don't you think I'm asking exactly the same question as what do we know is true right before line 2 executes? Because those two lines are sequential. Okay, so the post condition of line 1 is the same as the precondition of line 2. They're just different names referring to the same thing. Okay, so we look at what line 2 is going to do. Line 2 is doing one really simple thing. All it does is to say, oh, y now becomes 2. So the post condition of line 2 is really just, oh, okay, x is not affected, so x still has a value of 0, but y is changed to a 2. So after line 2, the post condition of line 2 is we know for sure that x equals to 0 and y equals to 2. Does that make sense? All right. So you guys might be thinking, well, but we can get the same thing from a trace, okay? Because we just fill in the column and the cells in the trace, and we can come to the same conclusion. So the tricky one is, what about line 3? What is the post condition of line 3? Well, if you use the pattern of, oh, we just have to append, we just have to say, and x equal to 5, then we have a problem. Because x cannot equal to 0 and x equal to 5 at the same time. That is just not possible. So that means we need some kind of a mechanism to forget that whatever value is in x when we overwrite x with a value of 5. So that's why I invent a notation called forget. So when we use the method or the function forget, the first one C is a condition, the second one is a variable. All it does is to look at the condition C and remove anything that mentions the variable v. That's all it does. Okay, it simply says, okay, whatever we knew about variable v, let's forget that because variable v is changed. So we cannot maintain what we knew about v. So in this case, the way we apply it is to say post 3 is forget post 2x and x equals to 5. So let me explain this step by step. The first, let me scroll the screen up so everybody can see it. So this basically says the post condition of line 3, which is what do we know that has to be true after line 3 executes, is based on what we know about post 2. But anything in post 2 that mentions x, let's get rid of those because x is going to be changed to 5. So whatever we knew about x before line 2 probably is not going to hold anymore. So post 2, we have already figured out a little bit earlier, which is x equal to 0 and y equals 2. And we have to forget everything about x. So that means after we apply the forgetting, the post 2 only has one thing remaining, which is, oh, y equals 2, because x equals to 0 has to be forgotten. Is that okay? Exactly. So we exclude what we knew about x in post 2 because we are about to change x in an irreversible way. So now, but the other part that we're adding is now that x equals to 5, we're going to say and x equals 5. So after everything is applied, this is just an easier way to look at the whole thing. So after we apply everything, the result is y equals 2 and x equals 5. So this is what we need to do to kind of track down what happens to a variable when we have constant assignment. So now we move on to the last one. Then we also have to say that post 4 is the forget of post 3 y, which means whatever mentions y in post 3, forget it, which is this portion here. But we also know that y gets a new value of 1, so we have to say and y equals to 1. So after we apply, or after we substitute post 3 with what we had here, then we apply the forget operation. This mentions y, it has to be forgotten. So x equals 5 is the only portion that is remaining from post 3. And then we use a conjunction to say and y equals to 1. Okay. So I know there's a lot of notation involved here. Okay, we have a forget function here. Okay, which is kind of doing exactly that. Okay, you give it a condition that mentions all kinds of variables, and then you have to tell it, oh, anything that mentions this particular variable, you know, forget that. Okay, you erase all of those. Yes, right, right. This explains how we can derive the post condition based on the precondition. Correct. Right. We are going step by step, statement by statement. Okay. Now, this one is something that seems to be completely redundant because a trace could have done this also. Okay. So next, we're going to move on to something that a trace cannot easily do. But before we go, on to the next topic, we just have to say something like this. X, E, and N are all placeholders, which means X is just a placeholder for a variable. E is a placeholder for an expression that does not mention the variable on the left-hand side of the equal, and then N is just a line number. So in this case, the post N is forget pre-N X and X equals to E. In other words, we are about to change variable X in the irreversible way, and I'll talk about what is irreversible. And as a result, whatever we knew about x before line n, we have to forget. But on top of that, we can now say, okay, but from here on, x has the value of e. Okay, are we doing okay so far? All right. So the notation can be difficult to grasp, but it is important to know what it is supposed to be doing first. Okay, so the reasoning is important. So now we can So if there are any chainable equalities, you should try to get everything resolved to constants whenever possible. For example, let us consider the following post condition. So this, I'm not telling you why, okay? I'm simply telling you this is true. The post condition of line 1 says x is less than y and y equals to 10. So what this means, okay, if we want to re resolve references to constants is we need to change this y to a 10. So the whole thing becomes x is less than 10 and y equals to 10. Okay? Whenever you can whenever you can change a variable to a constant, do it. Okay? So now the next topic is talking about self-referencing assignments. So now we throw something into here where we have x equals to x plus 3, y equals to y minus 1, and so on. And I believe that I probably forgot one statement at the beginning. Yes, I did forget one statement. Darn it. Okay. So let me fix that first. I need to look for anchor, which is self-assignment 1. So give me a moment to change that. I thought I fixed it, but obviously I did not. It is supposed to have one extra line of x equal to 0 first. And all the line numbers are off. Oh, this is going to be bad. because all the lines are going to be off by one. Don't know exactly what to do with this. Okay, so we'll go ahead and just kind of go with this. And then we give it some time to bake before we refresh the screen. So let me go back up. So the text description is probably off. Okay, so I'm gonna have to redo the text after this, but I'll go over the verbal explanation first, and then I'll go back and fix the notes. It's still being baked. There we go. Okay. All right. So now we're gonna work on this on the whiteboard, and obviously whatever I do on the whiteboard is not recorded, or I can do this in a way that can be recorded. Give me a second so that I can do that. Um, mouse pad. There we go. Alrighty. So we can now get rid of this. Okay, there we go. All right, so we're going to start with pre-1, and since I did not tell you anything about the precondition of line 1, pre-1 is just going to be true because true as a constant is the simplest thing that is always true. It doesn't say anything about any of the variable, but as itself, it's a value that is always true. So now we look at post 1, which is the same thing as pre-2. So with that one, we basically use this equation or this format, which is basically saying since we're going to change x irreversibly to a 0, then we have to say forget everything in pre-1 that mentions the variable x, but now we can also say that x equals to 0 as a post condition of line 1. Okay, does that make sense to you? Because we are changing x in an irreversible way. Irreversible means after line 1, there's no way to know what x was before line 1. Okay, that's what I mean by irreversible. And there are some changes that are reversible. This one is not. Okay, so now we say, okay, fine. What is pre-1? Okay, so now we say forget, not forgot. This is forget. Uh, this is just true. And does the expression true mentions anything about x? I mean, just visually, does t mention anything about x? Nope. Okay, so that means there's really nothing to forget. So after the forget operation, we get true back. And then we have true and x equal to 0. And based on what we discussed a little bit earlier on the whiteboard, we just get, oh, okay, so we just end up with x equal to 0. In other words, this is a fancy way to say after line 1 executes, we know for sure that x equals to 0. But this is a very mechanical way to derive it. Yeah, it's a mechanical way to derive the same thing. We want things to be as mechanical as possible because anything that is really mechanical can be programmed. Yep. hmm So now we look at post 2, okay, which is the same thing as pre 3, and we apply the same thing because we are also changing this time local, not local, we are changing variable y in an irreversible way. So now we say, okay, everything that is in post 2, or let me see, post 1, pre 2. So everything that is in pre 2, anything that mentions y, let's forget that. But on top, we now know that y equals 2. So now we expand it. Okay, so now we have to look at what is pre 2. Well, pre 2 is just x equals to 0. We forget everything that mentions y. Okay, so now we focus on this particular condition here. Does that mention anything about y? Nope. It says x equals to 0, but does it mention anything about y? Okay, so that means that there's nothing to forget. So after the forget operation, we get x equal to 0 again because there's nothing that it mentions about y. But now we know y equals to 2. Is that okay? So up to this point, it's a reapplication of what we learned earlier. The next one is going to be interesting. Okay, x gets x plus 3. So now the question is this update, x gets x plus 3, is it a reversible change or is it an irreversible change? If I know the value of x after line 3, can I reverse and reason what the value of x was before line 3? I'll give you a scenario. Okay, so let's just think of a scenario. And after this, I'm going to take roll first. So let's think about a scenario. So let's say for whatever reason, okay, that does not work. So I'm going to put it here. So let's just say that post 3 is, um, for whatever reason, it is not, it doesn't have to do with this code here, or it only has to do with line 3, but not the lines before. So let's say, after line 3, we know x has a value of 46. We don't care about y at this point because we're focusing on x. Okay. Line 3 is still the same as what you see on the board. X gets x plus 3. So what this means is we know, okay, for whatever reason, that x equals to 46 after we add 3 to it. The question is it reversible? Can I use post 3 to go back and say, I can reverse my step back and say that x is something before line 3? Can I deduce that? In other words, after adding 3 to x, it becomes 46. Can I reverse the process and ask what x had before I added 3 to it? What do you think? It is reversible. And what would be the precondition of line 3 if the post condition is x equals to 46? 43. That is correct. Okay. So that's why, this type of assignment is called reversible, meaning if you're given the post condition, you can always reverse the step to go back to the precondition. It's a reversible operation. Are we doing okay so far with the concept of reversible? Okay. So line 3 is reversible, line 1 is not. Because line 1 simply says, I don't care what the value of x was before line 1. From here on, it becomes 0. There's no way I can look at the new value of 0 to reverse back to what it was before line 1. But line 3 is reversible. If you tell me the value of x after line 3, I just go like, oh, if I subtract 3 from that value, that would be the value of x before line 3. And that's why it's reversible. All right, so we'll take a short pause right here, and then we go to take roll. Okay, so let me just make it visible to you. This is for today, which is February 19th, and the access code is algorithm, all in lowercase. Algorithm, algorithm, in all lowercase. All right, and what does it mean? What does the word algorithm mean? I explained that in one of the classes already. I just want to see if you guys remember. Hmm. It is a method, basically. It's a way of doing things. So if you look at the word algorithm, okay, and here we go. a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. Instructions to a computer, so to speak. And you will see this word quite more often, once you get to a 4-year university. All right. So are we good? Does anyone need more time for taking roll? Nope. Okay. Alrighty. So now we go back to our discussion earlier, okay, which is this part, and we're going to work on this. Okay. So now the question is, how do we specify post 3? Hmm. Okay. So let's see. Post 3 is the same as pre 4, okay? So now we cannot use forget, okay? Because forget means we are losing a lot of information. We don't have to lose that much information. So we look at this and go like, how can we do this? So let's read the notes, okay? So I just wanted to use this to prompt you to read the notes about how what to do when we encounter something like that. So let me just have you guys focus on f of 3 equals to x plus 3. Is this notation okay? Does everybody understand this is a definition of a function f? F of x is really just saying that x plus 3. Are we doing okay so far with that notation? Okay, it's a function notation in mathematics. So if this is a function, it is it's reversible. Okay, we just talked about how it is reversible. So the reverse operation is called the inverse function. So in this case, the inverse function, which is denoted by f with a how do you call that? It's not superscript, right? So f superscript -1 is the notation of f inversed. So f inversed of x is x minus 3. That's how we reverse the operation. So we'll focus on just these two concepts first. First, we define a function, which in this case is simply f of x is x plus 3. I'll be okay with that concept. All right. And then we define another concept, which is called the inverse function. The inverse function only applies when a function is reversible. It describes how to reverse the effect of f. So if the effect of f is to add 3, then to reverse it, we have to subtract 3. Is that okay? Are we okay with that? All right. So now, then the next question is exactly how is an inverse function defined? So the way we define an inverse function is we need the application of the inverse function to the function f of x. We need to make sure that this goes back to x. That is the property of an inverse function, a function and its inverse. In this case, f is the function. F inversed, which is denoted by f with a superscript of -1, is known as the inverse function. So let me just ask, are we okay in terms of the concept of a function and its inverse? One is to do something, the other one is undo, okay? So now the question is, can I prove that if I define f of x to be x plus 3, and I define x inverse of x to be x minus 3, can I prove that? What do you guys think? What would entail that proof? How would you do it? We just apply it, right? We just do a whole bunch of substitutions. So let's see how we can do this. Okay. So we now say f inverse of f of x. Now you can expand f inverse first, or you can expand f first. It doesn't really matter which one you expand first. So I'm going to expand f of x first. So I still have to apply f inverse on the outside. And can someone tell me what is f of x by definition? It's just x plus 3, okay? So we have x plus 3 here. Is that okay? Is that okay? Okay. And now what does f inverse do? F inverse is going to apply whatever is inside the parentheses and say, let's subtract 3 from that thing. So in this case, it would be taking x plus 3 as a whole thing and then minus 3, subtract 3 from it. Is that okay? Does everybody see how I applied function f and also f inversed the inverse function? Is that okay? Are we doing okay? All right. So can someone apply algebra and tell me what is the answer of x plus 3, the whole thing, minus 3? It's just x. All right. Well, I think I have just proven this thing here. In other words, I have proven that the way I define f and the way that I define f inverse is correct. One is the inverse of the other. Does it make sense? Okay. So now the question is, um, so what do we do in this case? Okay, when we have the code looking like this. And let me go back to my notepad here. Okay, so we look at this and go like, well, we know this has something to do with post 2. Okay, so we know post 2 is somehow involved in this process. Okay, post 2 is just this thing here. We know that right after line 2 executes, x equals to 0 and y equals to 2. The question is, what do we do about that? Okay, so this time we use a substitution. So this is basically substitution. Sub means substitution. So the question is, when we are substituting, we have to specify what we are looking for, and then what do we replace it with? Okay. Well, if you look at line 3, it doesn't have anything to do with y. So it doesn't make sense to look for y and then replace y with something. But it does something with x. So I think we need to look for x. Oops, wrong keyboard. There we go. And now the question is, what are we supposed to replace x with? Hmm. What about f inverse of x, which is x minus 3? Okay. In other words, what this is saying is everything that we knew about x is still true. However, every time you see x, you need to replace it with x minus 3. Because what line 3 is doing to x is to increase the value of x by 3. Are we doing okay so far with that concept? So x minus 3 is really just the inverse function. So now when we look at this, then we expand the whole thing. So the first thing is we expand what is post 2. Post 2 is x equals to 0 and y equals to 2. We look for every occurrence of x and replace every occurrence of x with x minus 3. So now we perform the actual operation. So we look at, okay, I'll do the kind of more systematic way. I copy and paste the condition itself, look for occurrences of x, which is right here, and replace it with x minus 3. And that's it. So essentially, this says what I just mentioned a little bit earlier. What we knew about x is still true for the most part. We just have to reverse the new value of x back to what it was before line 3. That's what the x minus 3 is doing. Is that okay? So you look at this, and for those of you who have taken algebra, you go like, oh, I know what to do with this with algebra here. I can turn this into just x equals to 3, and then y equals 2 is fine. Is that okay? Does everybody understand why x minus 3 equals to 0 is saying exactly the same thing as x equals to 3 using algebra? Okay? So this is a really interesting twist to the whole thing because we're not forgetting anything. Instead of forgetting something, we use substitution. And the way we apply substitution is to look at the right-hand side of the statement as a function, and then we look for the inverse function to reverse the operation and say, okay, whatever was true about x is still kind of true, but we have to reverse the new value of x back to what it was. then we can maintain the relationship that it had with the constants that we knew before. Okay, so I'm going to pause and see if you guys have any questions about this. Okay. Mm-hmm. Mm-hmm. Okay. I Yeah, remember I have to fix the notes too because I thought I fixed it, but I did not. Okay. So we'll finish the whole thing. Okay, we'll look at post for, which is the same thing as the post of the entire thing. Okay, so we'll just go like, okay, this is again, it's a substitution operation because y equals to y minus 1 is reversible. Okay, so how do we reverse y minus 1? So y plus 1, exactly. Okay, so in order to reverse the subtraction of 1, we just have to say plus 1. So now the substitution applies to the precondition of line 4. Look for occurrences of y and replace every occurrence of y with y plus 1, which is the reverse of y minus 1. Okay, so what this is basically saying is whatever we knew about y is still sort of true, but before we um, relate y to anything else, we have to reverse what line 4 did to y. And because line 4 is going to subtract 1 from y is now 1 less than what it used to be. So that means in order to maintain how y relates to everything else, we have to add 1 back to the new value of y in order to maintain its relationship with everything else prior to line 4. Okay, so now we do the substitution. So pre4 is just this portion here. So I'm copying and pasting here on the screen just so that you know what is the expansion of pre4. We just take whatever we knew about pre4 and just stash it here. And we're still looking for y. We place all occurrences of y with y plus 1. And now we perform the actual operation. So if I have access to an editor, I would have done this. Just copy and paste, and everywhere you see y, you replace it with y plus 1. That's substitution. And now you guys go like, oh, okay, but I know algebra. I can make this look cleaner. And you definitely can. So how do we simplify this? Y plus 1 equals to 2. If I need y to be by itself on one side of the equality, what do? We subtract 1 from both sides. Okay, so y equals to 2 minus 1, which is just 1. Okay, so you can see how algebra is actually kind of important in this class. All right, so we come to the same conclusion as we would otherwise using a trace. In other words, I have not shown you any evidence that this is a better way of doing things. Okay, up to this point, right? Um, we have, unfortunately, we lost Monday. So over the weekend, you can read this material. But more importantly, because we are running out of time today, more importantly, over the weekend, I really need you guys to focus on exam one from last fall so that on Monday, next Monday, I will go over the exam from 1999. Um, and then 1 week from next Monday is going to be your exam one. Yeah, so that's our first exam. It will take up the entire lecture period. It's open book and open notes, okay? But everything has to be on dead trees, like paper, okay? So if you have been taking notes on the computer or on the tablet, you need to transfer whatever is applicable on paper and bring paper with you on that day. So I will not allow electronic devices on the day of the exam. So is that okay? But otherwise, there's no limitation as to how much you can bring with you. If you say, okay, but Tech, I found this really great textbook that I think will help me, bring the book, okay? If you say, okay, I know this person who took this class from you exactly in 1999, and I have that person's exam one, well, bring that with you too. I don't mind at all, okay? Because your exam is guaranteed to be different from the previous one. or previous ones. Okay, so bring whatever you need on paper with you. Okay, and prepare for that. But that's, remember, it's not next Monday. It is the Monday after next Monday. So next Monday we'll talk about the exam that is already in the announcement, and then 1 week from next Monday is your actual exam date. All right, so we are out of time. Have a nice weekend. I'll see you all on Monday. And I have my own assignment, which is to fix the notes so that all the line references are correct. Alrighty, stop recording.